Hi, my name is Igor Slipicevic, and I have chosen case study in auto industry to be my final project for the deep learning course on Harvard. The technology I will use is Keras using TensorFlow API, and I will build a regression model to predict the car price. We'll use 3 layers in the model. I have found one data set on Kaggle that has around 11,000 records and 14 different dimensions that the model will be trained on. The working example will have a complete data set, summary sampling and partitioning, some data cleansing, splitting data into train and test data sets, and finally one hot encoding for the columns with the categorical values. The data set has these dimensions, has a make of the car, the model, year, engine fuel type, engine horsepower, engine cylinders, transmission type, driven wheels, number of doors and vehicle size, vehicle style, highway MPG, city MPG, popularity, and MSRP. So number of these are actually categorical values. You can see that model, make, year, engine fuel type, they are all categorical values which need to be converted to a numerical in order for the neural network to work. So my detailed code looks something like this. Hi, so here's my Jupyter notebook, and it's the code behind. So firstly, I have imported number of libraries from the Python, Keras, NumPy, Pandas, and essentially I've used the data frame Pandas to get the data, and then in that data frame I've done a bunch of transformations. So here's the list of the columns in the data set or data frame, and all those numeric values, columns with the numeric values, I have converted to a numeric values because they came as the text, and only 6 of these or 5 of these columns have numeric values: engine HP, horsepower, highway MPG, city MPG, popularity, and MSRP, which is the price, and which is the goal of this basically test or model to predict. Afterwards, I have normalized these values, and I've simply just divided those values with their max value in the columns. So, for example, if the value of the horsepower engine was 350 and the maximum value was 700, when divided it will give you 0.5. So below is the first 10 rows of the data frame with converted values and normalized values for those 5 columns that are identified as numerical. So you can see that all these values are simply now between 0 and 1. So we do have a whole bunch of columns with categorical values such as make, model, year, engine fuel type, etc. So in order to do that, in order to build a model, we have to one-hot encode them, meaning that to convert categorical values into numerical corresponding values. Before that, what I did, I have simply divided the data set into input data, which is an X, and a label, which is a Y, which is what we are trying to predict, which is our 14th column, which is MSRP. So now the input has these 13 colors without the MSRP. Let me execute this code because I haven't. I've done this and I've done that, and numerizing and splitting, testing, and now this is the function to one-hot encode the columns. Pandas come with a handy get dummies function which does exactly that. What it does, it essentially creates a separate value for each categorical value found in specific column. So for example, if we had a make of the model, make of the car, such as Acura or Alfa Romeo or Aston Martin, this function would create a separate column with zeros and ones when that occurrence has been found. So now instead of the 13 columns in my data set, I have close to 1050. So these are, oops, forgot to execute this. So this is now those columns, and we can see that it's created a new column for every single categorical value. For example, in vehicle style, it now has convertible, vehicle style, convertible SUV, vehicle style, coupe, etc., etc. And it has 0 and 1 columns based on their occurrence. And now we can see that it has 1049 columns in the data set. That does not impede or slows down the model in any way, shape, or form. The model executes just fine. We can notice that the model still, the data set still has the original 10 columns, which need to be removed from this data set. So this is what I've done here. Just removing those 10 columns, and now I have these numeric ones which I will need, and the rest is those created by the one hot encode function. Now I'm going to create train and test data set. For the training, I'll use 80% of the data set, and for testing 20. I basically just found the length of the data frame and multiplied by 0.8, which is basically this variable, converted the variable to the integer, and then I chose it can give me for the data from 0 to t, and similarly for the test. I need to convert these data sets now to NumPy array, because that's what we need in Keras to build a model. This is a function I use to build a model, and you can see that it has 3 layers, 64, 32, and one final one. I'm using ReLU as activation, and the optimizer I'm using Atom optimizer, and for the loss I'm calculating MSE, and for the metrics I'm also adding mean absolute error and mean absolute percentage error. Since the dataset is not that big, I'm going to use the k-fold validation, which basically partitions the data and uses one data for the training and keeps the others basically interchangeably uses those partitions to test and train. What I did here, I created a couple of arrays to store those intermittent mean square error history values and mean absolute errors. Here's the code, and now this will process the whole data set. So it will take some time to do it, and I will show later what was the result, but in essence, here's we can see that from my previous run, the saturation or overfitting happens almost at the 10th, 5th, 7th epoch, meaning that we can safely stop this model running after the roughly 10th, I would say. This is the smooth points curve, and this one is kind of showing it is close to the 40th epoch, but it's really not the case. It's really around 8th or 10th epoch that we can safely stop. Similarly, the mean square error history also shows the same findings. At the end, I have evaluated the model and I print the scores once the model is evaluated using the test data. And here are the results. We can see that the mean square error is quite low, 0.00036, which is really good result and shows that my model correctly predicts the price. That's all for me. I hope you liked it. Thank you.